Hello everyone. Today we'll present a paper about return-oriented programming gadget catalog for the Xtensa architecture. The agenda consists of introduction, where we'll explain the nature of the ROP and general concept. Then we'll talk about Xtensa architecture itself, its specifications and main features. Later we'll cover the actual work of the paper and gadget catalog creation for the Xtensa. In the evaluation part, we'll evaluate the performance of the gadget catalog creation. And in conclusion, we'll have a look at the achieved results. Xtensa is a 2-bit RISC architecture. It was designed for embedded systems. It has configurable cores. Xtensa is highly configurable. Its configurations are used for application-specific cases, which increase the overall performance. Xtensa supports 2 application binary interfaces, called 0 and windowed. In our case, we have chosen windowed API since it's more interesting from the scientific point of view, because it uses window sliding mechanism, which makes the process of crafting payload much more complicated. For both APIs, we have important registers, A0, which is used as a return address, and A1, which is used as stack pointer. So the ROP, in general, ROP exploits the buffer overflow vulnerability. Buffer overflow vulnerability, it's a necessary precondition for the ROP exploitation. And it overrides the vulnerable function's return address on the first address of the first gadget. Gadget is a block of instruction sequences with a return instruction at the end. Instruction sequences are located in a subroutine of an existing program or in shared libraries. In the following figure, we can see the gadget that at the end is a return instruction, which redirects the control flow to the beginning of this next gadget. With this kind of structure, they're forming the gadget chain. After overflowing the buffer, gadget addresses are overwritten in the stack. Gadget addresses are pointing to the actual instructions in the code segment. In Windows API, we have 16 logical registers, 32 or 64 physical registers, depending from the configuration. And the window slides on 4, 8, or 12 registers using the following functions. Rotation size is defined by return address top 2 bits. Enter instruction shifts the window, and redouble instruction shifts the window back. So in the following figure, we can see that we have logical registers and physical registers. Logical registers are mapped to the physical registers, and after we are executing, for example, call for function, the window rotates on 4 registers down, and so so logical registers becoming to map to other physical registers. Also, it's important to note that this kind of structure allows caller and caller to exchange arguments in overlapped registers. In this case, overlap registers are physical registers starting from the AR4 to AR15. So, and here, yeah, AR4 to AR15. So they are shared between caller and callee. This kind of structure eliminates use of prologue and epilogue. And overall, it improves performance and code density. Let's, in Windows API, we have 2 mechanisms called window overflow and window underflow. Window overflow occurs when there is no physical registers are left. Overflow exception handler saves registers values to the stack. We have 3 different overflow handlers for 3 different calls. Window underflow is a reverse operation to overflow invoked by redouble instruction. Underflow exception handler loads register values back from the stack. We have 3 different underflow handlers for 3 calls. So the main idea is that window underflow saves registers values to the stack, and window underflow loads these values back from the stack to the register window. Let's have a look on the gadget chaining concept on Xtensa. For the gadget chaining, it's enough to manipulate with the return address A0 and stack pointer A1. Return address is used for jumping to the next gadget. Stack pointer points to the next gadget exploit stack frame. And underflow exception handler loads fake register values from the stack into the register window. In the following figure, we can see the order and structure of the gadget chaining. And it's also possible to use registers starting from A4 to A7, or even registers from A4 to A11, but with different underflows. But overall, the structure should be preserved and strictly kept. Let's have a look on the stack layout example for underflow 8. We have a simple program, main 4-bar bus, they're invoked subsequently. And in the bus function has memory buffer overflow reliability. And the same program is represented on the stack layout. It's important to say that the order of the frames is strictly should be kept. Here you can see that function frame consists of extra safe area, ESA, of the current function, and base safe area of the previous function. ESA consists of registers of A4 to A7, BSA from registers A0 to A3. Storing BSA of the previous function allows us to backtrace to the previous frame, and this kind of structure should be preserved during the crafting of the rope attack. A memory-based way of passing values is persistent and allows to pass values between non-neighboring gadgets. If one gadget wants to pass values to another using memory, it's necessary to save the value to the target's gadget stack frame. The underflow exception will load this value from the stack into the register window. Then the value eventually will be used by the target gadget. Let's have a look on the gadget catalog creation. First of all, let's define what columns are meaning. The present column contains values that will be loaded into the register by underflow exception. The assembly column shows the gadgets, which basically are instructions of the Xtensa. The condition columns defines conditions that gadgets need to fulfill in order to be chained. So it's basically some sort of restriction on the indexing. So which register can be used? Yeah. So let's have a look on the store operation, which stores the constant to the target address. During the present phase, we are storing our constant to the one register, to address to another, and S32 instruction saves the value, takes the value from the register AI and saves to the address stored in the register AJ. Let's have a look on the load operation, where it loads from the address to the certain variable. There is again here during the present phase, we are assigning address where we need to load to the register AG1, and the address where we need to save, the address of the variable where we need to save to the next instruction, registers AG2. Here it's the key point that passing of the value from the first gadget when it after it loading. So it's loading from the address to the register AI1, and this value is passed using the overlapped register to register AI2. So the idea is that after the load instruction, the red double instruction rotates the window, and the same register can be invoked by using another index. The index can be calculated using this simple formula where it's addition of the first index with the rotation size. So let's take example that AI equals to 2 and our window rotates by 8. So the index of the store operation should be 10. If the following condition meets, the load operation can be done. Let's have a look on the addition, subtraction, and multiplication operations. So we need to add two values and save the result to the value of V1, to the variable V1. In the present operation, we're assigning our values, and the addition operation, it adds takes two values and stores them in the following register. Then read W instruction invokes and our window rotates, and this register can be accessed from the next operation, but using other index. The index again can be calculated by using this formula, and if this restriction is kept, then it's possible to access. Basically, just like passing values using the overlap registers. So this value sum of two variables are stored, are saved to the address of the first variable. Yeah, and this simple solution works for the addition. Subtraction and multiplication is similar. Only operation instruction should be changed to sub here or to mul. Oh, let's have a look on conditional jump, which is much more complicated, where we need to compare two values. And if two values are equal, then we need to jump to address 1. In our case, we're going to address 2. So the idea is that we need to subtract one value with other value. If we're getting the 0, then we're jumping to address 1. Otherwise, we're jumping to address 2. Let's have a look on the implementation. We have here 5 gadgets: sub, store, move with, store, and read. During the present phase, we are storing two values, two values of the variables into the following registers. Then we are performing the subtraction operation, and the result of it will be stored into the AI1. Then our window rotates. This value can be accessed using the following register, but with other new calculated index. So this subtraction result can be stored to the address of the registers of the request register AZ3. So we are saving the result of subtraction to this following register, and here all the move with it performs this kind of logic. It checks if the value in AZ3 is equal to 0, then it uses it uses the address of 1, address 1. In other case, if the value is not equal to 0, the address of 2 is saved, replaces the address of 1 into the following register. Then this following register can be accessed after window rotation using the other index. The index is the same, it's calculated using the simple function. And this address, like if it's accessed here, we are storing this address into the we're storing the address into the appropriate place where later on we can just jump to it using the redouble instruction. So I know it's complicated, but have a look on the pictures. So this the same, like jump we need to compare to and to jump to address 2, otherwise to address 1. We divide it into 4 steps. The first one, sub, it subtracts 2 values. If the result equals to 0, then moquis operation saves the address 2 to its register A2. Otherwise, moquis saves the address 1 to its registers A2. So in this case, S32 instruction saves the address in A2 to the next gadget stack pointer SP4. So like moquis, it's choosing which address should be placed into A2, then save operation. It saves to the SP4, and later on, this simple ret instruction just jumps to the appropriate address, either address 1 or address 2. Let's have a look on the evaluation part, where we can see number of useful gadgets. In our example, we got 159 gadgets found in simple Hello World application on the right operating systems running on the ESP32 microcontroller. Generally, 2 rules were applied to gadgets. That gadgets should have a single control flow, and if the gadget has additional instructions, they should not affect to the needed registers. So for the number of found gadgets for the appropriate function is given. But we need to keep in mind that S32 instructions has a special importance since they are used for all operations to write the result to the location of a variable. So if you wouldn't want to use any of them, for example, load, so later on we need to save its result after loading to the appropriate place. So we need to use S32 operation, and S32 operation with the following condition. In our example, we found only with the index equal to 2. So I1 equals to 2. So it means that we are looking only for gadgets which are writing to the register A2. So we found out that we are using the index 2. So we're needs accordingly register A2. So this row shows all operations which are writing to the register A2. We can see that only 8 of 51 number of found gadgets for L32 is writing to A2. So generally, we can see that we have all of them except XOR, which write to A2. So let's have a look, like what's the idea behind. So like if all of them are writing to A2, then later on, this value can be accessed via, after rotation of the window, via overlap registers, if the window shifts by 8. So this value stored in A2 can be accessed using the register A10 if window shifts by 8. And later on, it can be saved to the any desired location. We just need to put the address where we want to store here. This table shows implementation of the gadget chains with the gadgets of the application. It shows which underflow exceptions can be used to jump to that specific gadget chain. The number of words of each of the operations uses in the payload is also given. So we can see the size, how much it takes in words, yeah, for the appropriate operation. For a store, we can see it needs 4 words, for load 7. This includes the gadget's address, the point to the next gadget, and the preset values for each gadget. Let's conclude the result of our work. The creation of a ROP gadget catalog for the Xtensa architecture is possible. We have proved it. So even a simple program which we use Hello World contains most of the necessary gadgets needed for construction of the exploit. Of course, there might be other combination of gadgets that fulfill the requirements of the gadget chaining schemes. Thank you for your attention.